The audiobook reviewed here is The Structure of Scientific Revolutions by Thomas Kuhn. In the preface, Kuhn tells us that he began the work as a way of explaining to himself and his friends why he chose to study the history of science. In the preface, he describes the work as an essay, and that he had hoped to include additional material in order to compile a book. He mentions the many people that influenced his thinking, and amongst these were Paul Feyerabend. It was perhaps unsurprising that Feyerabend would have been an influence, as they were based at the same university and shared common interests. However, for the most part, I have been a little sceptical of the ideas presented in Feyerabend's Against method, and have made some attempt to address them elsewhere. The sharing of some similar themes is evident later in the book. Already in the preface, Kuhn approaches a very sensitive subject area by marking out the social sciences, as opposed to the natural sciences, for special attention. However, here he makes it clear that the practitioners of the two share similarly permanent answers to the questions posed within their science, while in the same paragraph drawing attention to controversies over the fundamentals. Such controversies, however, are more a reflection of the relative simplicity of the fundamental phenomenon being described in each of the disciplines. While in the fundamentals of one branch of physics, mechanics, there is consideration of the motion of bodies in an idealized environment. In psychology or sociology, the fundamentals are concerned not with inanimate, idealized objects, but richly complex human beings. That fundamentals should be arrived at all is testimony to the skill of the practitioners in those fields where matters are complicated not only by volition, but also by the complex genetic coding resulting from 3 billion years of evolution, multi-layered environmental influences, and the interplay between all of these, not just in the individual but in group and society settings. Perhaps the benefits to society of the technological advances informed by the natural sciences are the real reason why the natural and social sciences are separated. To propagate the arguments within the social sciences, various distribution media are needed: the printing press, the internet, the radio, and so on. These medium, however, are impossible without the associated manufacturing facilities, which in turn are directly dependent on an understanding of branches of physics or chemistry. Thus, rather ironically, one might suggest that the wider debate in social sciences can take place only because of the success of the natural sciences. This in turn can be reduced to, what can your science do, on a practical level? While there have been innumerable successes in the social sciences, wherever we turn in the modern world, we are faced with the end results of an understanding of the natural sciences. Bricks, paints, plastics, papers, ceramics, artificial light, electronics, metals, telecommunications, automobiles. Many of these have existed for millennia, but in the current age an understanding of the natural sciences is necessary for the mass manufacturing of such items for large populations. On the other hand, the evidence of the success of the social sciences is abundant, but altogether more subtle in manifestation, and more effort must be made to find this evidence. To reiterate, however, this dichotomy is altogether different from the process of doing science in these two branches of science, which I would argue reduces to a combination of empiricism and rational systematic investigation. Although creative methods and intuition can be used to arrive at solutions more quickly, it is the error-checking, rational, systematic and empirical investigation that validates the results and enables the foundations to be formed and built upon. There is thus a difficulty in focusing on such a dichotomy in the preface, even before the book is properly begun. Such debates occur rather artificially in various guises, but the generalizations necessary are such that the accuracy of statements is exchanged for the expediency of the immediate discussion. However, unlike Feyerabend, Kuhn contextualizes his statements by suggesting that his consideration of the issues led him to formulate the concepts of paradigms in scientific research, and indeed this becomes a central tenet of the subsequent work. Having listened to the audiobook version of Thomas Kuhn's The Structure of Scientific Revolutions several times, it has left me with the impression that this is a profound piece of work. Although Kuhn was very much influenced by Paul Feyerabend, having compared this work with Feyerabend's Against method, I found that many common themes are more fully developed in Kuhn's work. I also found that Kuhn's profound interpretation of science as a social function not only has authenticity, but that Kuhn's perspective offers the possibility of further interpretations from a number of different perspectives. Chapter 1 is a relatively brief chapter, or essay as he refers to it. In this chapter, Kuhn sets the scene. He hints at the validity of historical scientific paradigms which might be considered redundant in a progressive and iterative model of science. This in itself is sufficient for the reader to examine one of the common assumptions about science and progress. Indeed, such a perspective offers interesting insights into historical examples of scientific understanding. Kuhn also introduces the reader to the concept of normal science, as separate from the science that constitutes the paradigm-shifting scientific revolution. By this means he is able to point us towards the tensions that often occur when the scientific revolution meets normal science. By suggesting that the revolution itself does not occur at a certain point in time, but is instead a gradual process, Kuhn helps the reader to avoid obvious pitfalls. What I also found interesting here was Kuhn's suggestion that the revolution doesn't take place without a conflict between the two opposing camps. This itself is reminiscent of the Hegelian dialectical. However, in this chapter, Kuhn is merely setting the scene, and it is in the later chapters that his arguments are elaborated upon. Thomas Kuhn's The Structure of Scientific Revolutions, Chapter 2. In this chapter, or essay as he refers to it, Kuhn writes about what he considers to be the route to normal science. In this chapter he elaborates on his distinction between normal and revolutionary science, and it makes for interesting reading. Early in the chapter, Kuhn suggests that textbooks offer scientists a medium through which they can arrive at a consensus. He also notes that the road to a research consensus is extraordinarily arduous. The textbook states the common problems facing a research community. There were two features he suggests are necessary for revolutionary science. Unprecedented findings which were sufficient to draw people away from the other areas of study, suggesting that there was a competitive element to the process. 2. That revolutionary science would be sufficiently open-ended to enable others to develop theories from this. In other words, they would become stakeholders in the process. I applied the Darwin test on this. What I mean by this is that Darwin's theory of natural selection is so robust that for any philosophy of science to make predictions about science, they should hold true when applied to Darwin's theory of natural selection. For the points above, I hope the reader will agree that Darwin's work on the origin of species was both unprecedented, produced a very strong following, and also gave rise to an entire field of study which has been occupying scientists for the past 150 years. Kuhn then goes on to discuss revolutionary science in physical optics and with regards to electrical phenomenon. In both cases, he provides the reader with evidence that prior to the revolution there were many small areas of research founded on different assumptions or attempting to explain different phenomena. What comes after the revolution, in Kuhn's interpretation, is very interesting and I thought was very authentic. Thus he suggests that a language arises which can be readily understood by those outside of the research community, although this changes very rapidly. After a time, the community develops a specialized language. Those who ignore the revolutionary paradigm are, quote, bred out of the profession, unquote. The research community develops more specialized equipment to investigate ever more specialized questions. He also has some interesting things to say about different branches of science. Thus, for the social sciences, he suggests that the revolutionary paradigm may be occurring today, although this would have been some time ago when the book was originally written. However, such a grand statement should be qualified with more specific examples to support his argument. Another possibility is that the social sciences may operate differently to the natural sciences in terms of how research communities are organised, behaviours within the communities, and even the nature of the questions that are being posed. I would argue, therefore, that a much closer examination needs to be made in order to justify even simple statements of this type. The strength of his book lies in how he guides the reader from examples through to his conclusions, and there is no reason why this should be abandoned when discussing a very complex branch of science. When he refers to medicine, however, he makes an interesting observation that this is strongly driven by an external social need. He also suggests that in astronomy the first paradigms arose in prehistory, and no doubt he implies that navigation by the stars was a necessary skill for hunter-gatherers. He also notes that technology assists in gathering data necessary for the development of a science. For me, Kuhn's framing of the paradigm has another implication. My interpretation of Kuhn's paradigm is that it is a function of the minds of the scientists rather than a function of the underlying properties of the universe. In other words, revolutionary thinking isn't so much about a better understanding of the world, but rather one that is more successful engaging the scientific community. In Chapter 3 of Thomas Kuhn's The Structure of Scientific Revolutions, he focuses on the nature of normal science, and interestingly, gives due consideration both to qualitative and quantitative approaches. The core essence of this chapter lies in three tenets. 1. That normal science, within a paradigm, establishes significant facts. 2. That normal science attempts to relate facts to theory. 3. That normal science aims to expand upon theory. These key features of Kuhn's concept of normal science also preempt his later discussion of scientific revolutions. What is also interesting about this chapter is that Kuhn again relates scientific paradigms to social structures within the scientific community. For example, a successful paradigm will address some of the acute problems faced by the scientific community. Kuhn also makes a point about the complexity of nature being made to fit into the relatively rigid structure of a paradigm. While on the subject, it is also tempting to apply the same arguments to Kuhn's approach to paradigms, in the sense that this is a generalization about quite complex activities in a vast range of different sciences. This in itself deserves further reflection, as it would mean that the concept of paradigms, normal science and revolutionary science can be subject to the same iterative processes he suggests to apply to science itself, although strictly speaking this is philosophy. Kuhn has some interesting comments about those that do not work in paradigms and how such scientists are generally ignored by the scientific community unless they are part of a revolutionary movement. As with previous chapters, Kuhn offers the readers much to reflect on. Chapter 4 in Thomas Kuhn's The Structure of Scientific Revolutions is a fairly brief chapter, or essay as he also refers to it. In this chapter, Kuhn suggests that a scientific community solves puzzles. These puzzles are problems that need to be solved within a framework of rules. Kuhn suggests that the scientific community chooses puzzles that they think are solvable. Thus, there are the explicitly clearly articulated central problems lying within the informal framework of rules. As a result, seemingly straightforward amendments of solutions to problems do not work in the scientific community if they do not also address the surrounding framework of rules. Kuhn gives the example of a suggested amendment to Newton's inverse square law of gravitation, which would have enabled researchers to derive the orbit of the Moon from Newton's laws of motion and gravitation. The amendment was ignored by the research community, and other findings eventually enabled the derivation to occur without this move away from the central paradigm. Kuhn's ideas here form a profound basis for consideration of scientific activities. Such questions can be turned to specific branches of science. We can begin to ask about the rules that govern research in certain areas of psychiatry, for instance, or reflect on the meaning of the open science movement. We can also use these concepts to differentiate science from other social activities. Chapter 5 in Thomas Kuhn's The Structure of Scientific Revolutions is titled The Priority of Paradigms. In this essay, as he refers to it, Kuhn elaborates on the relationship between rules, paradigms, and normal science. I thought this essay was less articulate than the previous essays. although he introduces some important concepts, which he develops in later chapters. Kuhn suggests that rules govern a research tradition, and that there is a common understanding within the research community that forms the research paradigm. However, he thinks that scientists are often unaware of the specifics of the research paradigm, and instead rely on an intuitive understanding much akin to that proposed by Wittgenstein. Wittgenstein proposed that we know a game by its family of properties. Even if a game doesn't have all of the properties we identify with the game, we will still be able to recognize it as such through these flexible recognition mechanisms. He goes on to describe science as a ramshackle structure with little coherence, arguing that if we consider the physical sciences, we will see a big difference between related sciences. He gives the example of a chemist and a physicist being asked whether helium is a molecule and giving two entirely different answers. The explanation for this is that the scientists were using different paradigms, even though both branches were derived using quantum mechanics. I found many of Kuhn's suggestions profound. He suggests, for instance, that the scientist may undertake research quite separately from any explicit consideration of the underlying paradigm. This thought is quite remarkable, as it suggests that a scientist may dissociate a rational approach used in their experimental study from an irrational approach to the wider context of the research paradigm in which their study is operating. In other words, if there is an obvious flaw in the underlying assumptions of a research paradigm, then it doesn't matter how many well-designed studies are undertaken within that paradigm, the conclusions will still be erroneous because of the mistaken assumptions several layers down. Kuhn would presumably have recommended a healthy skepticism towards the research paradigm, although this is not explicitly mentioned within the essay. I can't help but think, in describing the research paradigm, Kuhn is actually describing in a roundabout way the characteristics of a social group. These characteristics remain invariant regardless of whether it is science we are talking about or any other group activity. The group will form an identity, and this identity is developed through a shared language and culture. The culture itself may develop from a decision to solve specific problems whereupon there is a concerted drive to use a systematic approach to achieve this end. In science, this results in the research paradigm. However, this will also be repeated in other parts of society, forming the impetus for social change across a variety of fields. The 6th chapter in Kuhn's book, The Structure of Scientific Revolutions, is titled Anomaly and the Emergence of Scientific Discoveries. Kuhn gives the example of Thomas Priestley and his discovery of oxygen. The discovery of oxygen is undoubtedly an important one. Kuhn playfully moves around the history of the discovery of oxygen, showing the futility of pinning it down to the discovery at a certain point in time by means of a simple act. Instead, he argues that there must be another means of conceptualizing this. The identification and characterization of oxygen occurred not in isolation, but in the context of contemporary theory. It was through the change in theory that the significance of oxygen came to be appreciated. In effect, it was a network of scientists that collectively brought about the discovery of oxygen, combining both the experimental and conceptual elements necessary for this accomplishment. Kuhn gives other examples. Continuing with his division of science into normal science and revolutionary science, he argues that normal science restricts the focus of the scientist towards confirmation. However, this very process highlights anomalies, and it is these anomalies that form the basis for revolutionary science. Revolutionary and normal science can be considered to be activities at different levels of a theoretical hierarchy. The implication is that even when activities are geared towards one level of that hierarchy, they lead necessarily to changes at other levels of the hierarchy, and perhaps in an unpredictable way. Kuhn gives the example of an experiment involving the presentation of playing cards to subjects. One of the playing cards would be distinct, but unless they were looking for this, the subjects didn't register it consciously. When they were challenged on this after the presentation, a small minority of the subjects would become confused about what they had seen, and Kuhn hints at what is to come later in the book. By looking at the material in this way, Kuhn offers us insights into the underlying mechanisms of science, as well as offering the potential to look at alternative approaches. The 7th chapter in Kuhn's The Structure of Scientific Revolutions is titled Crisis and the Emergence of Scientific Theories, in which Kuhn elaborates on the conditions which he suggests lead to scientific revolutions. He identifies several historically important scientific theories and examines the circumstances surrounding their acceptance in detail. Kuhn poses the question of how new theories are accepted in the place of older, more well-established theories. He gives the example of Newtonian mechanics and the occurrence of early advocates against an absolute model of space in favour of a relativistic model. However, what is interesting is that these criticisms were apparent only for a short while before disappearing from the scientific debate. Kuhn argues that this occurred because there was no crisis in science. In other words, the normal science which he discussed previously was not producing consistent anomalies, which would cause the scientists to question the validity of the underlying theory. As a result, there was no impetus to take this debate further until the late 19th century, when this became relevant to the contemporary debate in physics. Kuhn uses physics to generalise to science, whilst making no mention in this chapter of those branches directly relevant to the neurosciences. Nevertheless, it's interesting to note that in the neurosciences, several theories do coexist, which are currently relevant and which offer different perspectives on the same set of phenomenon. Kuhn's arguments hold relevance to a winner-takes-all approach to theory building, or else the neurosciences have been in a persistent state of crisis according to his arguments. This, though, doesn't seem consistent with the many practical benefits that these different theories have produced, and so maybe the neurosciences represent a branch of science which merit their own philosophy of science. The title of Chapter 8 of Thomas Kuhn's The Structure of Scientific Revolutions is The Response to Crisis. Whereas in Chapter 7, Kuhn focuses on how the crisis in science arises, in this chapter he elaborates on how the scientific community responds to this crisis. He makes the interesting point that in criticising one theory, the scientist must propose an alternative, otherwise this is not the pursuit of science. What is also interesting is that he suggests that when this competitive process ends, the branch of science becomes static, and in the example he gives it becomes a research tool. Kuhn suggests that there are always discrepancies, even in the most successful of paradigms. With a move towards crisis, there are increasingly divergent explanations, and there is a loss of identity within the field. Indeed, Kuhn maintains that all crises involve a blurring of paradigms. The crises are closed in one of three ways. In the first case, the crisis handled. Chapter 9 is titled The Nature and Necessity of Scientific Revolutions, in which Kuhn further discusses the nature of scientific revolutions. An important feature of this chapter is that Kuhn draws parallels between scientific and political revolutions. To support this analogy, he explains how within political organisations and scientific communities groups arise with significantly different values from the mainstream. The scientific communities and political parties are housed within the institutions, and the new movements are not able to successfully challenge within these institutions, but must instead separate with the support of their proponents. However, Kuhn is careful to distinguish between scientific and political revolutions. With scientific revolutions, there are fundamental features of nature at play which determine the course of events. For instance, the scientific paradigm is challenged by an anomaly which becomes a central feature of the new paradigm. The anomaly is a feature of nature, and the paradigm which successfully explains the analogy replaces the old paradigm rather than resulting from a cumulative change in the old paradigm. Essentially, there is a transformation of paradigms rather than a cumulative change. The logical positivists challenge this assertion by arguing, for instance, that Newtonian mechanics is a special case of Einstein's theory of relativity. Kuhn takes time to address this and argues that the restriction that is placed on the theory of relativity impinges on the utility of this theory under these constraints. Furthermore, the paradigm changes also extend to the rules governing the behaviour of scientists in the scientific community. The proponents of the different paradigms are unable to hold joint discussions since they operate within different frameworks with divergent views which cannot be resolved. The anomaly is therefore the determining factor in the competition between paradigms, and ultimately it is this anomaly which highlights the problems in the old paradigm and is explained in the succeeding paradigm, and this in turn is a feature of nature. I think this perhaps is the most significant differentiator between political and scientific movements, assuming of course that the properties of group behaviour are not deterministic, but instead are contingent on the interplay between the properties of memes, that is, ideas that are transferable between people, and the properties of the group. Even here, however, Darwinists would argue that these memes demonstrate selective fitness and are therefore subject to general principles, which with some work can be identified. Kuhn has also produced a very deep work, in one sense. A chapter such as this can be read repeatedly and still offer new insights. Kuhn has produced a very deep work. A chapter such as this can be read repeatedly and still offer new insights. The analogies themselves give the reader the opportunity to use their knowledge of parallel systems to further understand the central arguments. Feyerabend's Against Method, in comparison, draws on some of Kuhn's work but reduces the central argument to a simple premise which is significantly easier to challenge. The interrelatedness of Kuhn's chapters provides, I think, a stark contrast which hints at the gestalt that Kuhn discusses in the previous chapter. Chapter 10 of Kuhn's The Structure of Scientific Revolutions is titled Revolutions as Changes of World View, and is the lengthiest of the chapters. Kuhn continues his central arguments from previous chapters that scientific revolutions involve a change in perspective, and he writes that the scientist must learn to see a new gestalt. Indeed, after a revolution, the scientist must learn to see a new world, and the student of science is trained to see the world in this way. There are significant differences between these perspectives which are incommensurable. Kuhn draws a parallel with an experiment in which subjects were required to wear inverting prisms and learn to adapt to this new visual world. There is a transformation in their perception. He goes further and suggests that perception of scientific paradigms and visual perception share a similar underlying physiology. A similar analogy is drawn with the previously mentioned experiment involving anomalous cards presented as part of a sequence. Kuhn suggests that the evidence for these changes in perspective should be sought in behaviours, although it is also possible to examine the perceptual constructs themselves rather than behavioural proxies. Kuhn questions the assumption that the perception follows directly from the sensory observations as outlined in the highly influential philosophy of Descartes. He emphasises the importance of an understanding of the mind in understanding science, and asserts that there is an absence of a language of perception. Kuhn gives examples to support his argument, including the identification of atomic elements which resulted from a different perspective, rather than a focus on experimentation alone. Indeed, he describes John Dalton, who formulated the atomic theory, as a meteorologist rather than a chemist who approached some of the questions posed by chemists by using a different paradigm. Along the way, he replaced the affinity theory which had predominated up until that time. In this example, it becomes clear that the paradigm change involved a change in culture in which common assumptions were abandoned, where debate between highly regarded proponents of the different perspectives illuminated the core issues in the paradigm change, and in which a significant proportion of the scientific community would need to be persuaded of the advantages of the new paradigm. This chapter raises many questions and further defines the nature of the paradigm changes Kuhn refers to throughout. The 11th chapter in Kuhn's The Structure of Scientific Revolutions is titled The Invisibility of Scientific Revolutions. In this chapter, Kuhn revisits the themes developed in earlier chapters. He explains that the celebrated scientific revolutions that he uses as examples are selected solely that the reader is already familiar with them. Kuhn suggests in this chapter that revolutions are invisible because of historical revisionism in science textbooks. His argument runs along the following lines. Firstly, assuming that scientists and laypeople use textbooks as the primary source of learning about a scientific field, then the presentation of the field within the textbooks is of central importance. Secondly, Kuhn suggests that there is a central assumption that science is independent of the historical context. Note that he himself does not hold this view. Thirdly, Kuhn argues that when a revolution has occurred, there is a need to rewrite the science textbooks. This rewriting follows a pattern. Thus, the central problem which was solved in order to create the paradigm change is reframed as the only problem that existed prior to the paradigm change. The main scientific players are then described in relation to this problem-solving exercise. Fourthly, through this revisionism, science is presented as a cumulative endeavour whereby incremental improvements in solutions to central problems lead to the paradigm change. In this manner, the subtleties around the scientific revolution become invisible. Kuhn gives examples to support his argument about the importance of historical context in scientific revolutions. This chapter addresses an important criticism of Kuhn's central arguments, namely that scientific revolutions are portrayed as cumulative developments of scientific knowledge, rather than transformational paradigm shifts. Kuhn's response is to characterize the simplistic narratives as examples of historical revisionism, and he emphasizes the importance of context in interpreting scientific revolutions. Chapter 12 in Thomas Kuhn's The Structure of Scientific Revolutions is titled The Resolution of Revolutions. Kuhn suggests that those involved in scientific revolutions have characteristics which are different from those of scientists involved in normal science. Thus, he suggests that such scientists are usually new to the field and for various reasons are not under an obligation to operate within the boundaries of the paradigm, but instead are able to challenge the paradigm itself. He then goes on to talk about the validation of theories, and this gets quite interesting. Kuhn categorizes the validation approaches as follows. 1. Categorical. 2. Probabilistic. So the first question to ask about the validation process is whether or not a theory completely accounts for the experimental data. In a categorical model of theories, the theory would be expected to account for all of the data. However, this would be unrealistic, and Kuhn suggests instead that most scientists consider a probabilistic model of theory validation in which the theory accounts for most of the experimental findings. Another approach to validation of theories is also considered by Kuhn, contrasting 1. Identification of evidence for the theory, 2. Falsification. A theory can thus be validated by the identification of supporting evidence or by surviving attempts to falsify the theory with experimental observations which do not fit with the theory's predictions. The suggestion of a principle of falsification in science was developed by Karl Popper. Kuhn then refers back to anomalies in the experimental data which are sufficient to generate a challenge to the dominant paradigm. This allows the beginning of an appraisal of the paradigm itself, but it is only when the conflicting paradigm is developed that the necessary debate can begin. Kuhn then gives some of the characteristics of the subsequent debate which results in the resolution of revolutions. This is an elegant chapter, with Kuhn drawing together the threads from previous chapters into a narrative with powerful explanatory properties. Chapter 13 in Thomas Kuhn's The Structure of Scientific Revolutions is Progress Through Revolutions. Here Kuhn questions what it is that makes a science. He comments in an interesting way on what differentiates the branches of science. Thus he suggests that a strong sense of identity within a scientific discipline occurs when there is agreement within the community on past and present accomplishments. He also writes about the progress that occurred in the arts as representations became more realistic, with refinements in the instruments and techniques of the artist. The relationship between the scientific community and the paradigm is emphasized, as well as the debate that occurs between schools. Kuhn also suggests that although science progresses, it does not necessarily progress towards any specific goal. He also reiterates the effectiveness of scientific revolutions followed by periods of normal science in developing a body of scientific knowledge. However, he leaves the reader to answer the question, what must the world be like for us to know it? Kuhn's Postscript was written 7 years after the publication of his book. In the Postscript, he addresses many of the criticisms that have been raised against the structure of scientific revolutions, and it is therefore important for those wanting to come to a better understanding of his seminal work. Having written this over 7 years, Kuhn had a great deal of time to reflect on the criticisms levelled against his book and to further refine his understanding, which is evident from the text. Kuhn's work is subtle enough, but condensing 7 years of reflection on the responses to his work means that the Postscript is dense with complex ideas, and I don't think it is meaningful to say that it can be or should be easily summarised. The strength of Kuhn's work is not that it is didactic, but that it relies on the reader to engage with the material. Kuhn proceeds to move through the main criticisms of his texts. Paradigms are a starting point for the Postscript. Kuhn explains that the term paradigm has different meanings for him, which he utilises in his book. Indeed, one of these meanings is associated with a great deal of controversy. He writes that a scientific community has received a standardized training. Different schools settle their competitions quickly and professional opinion is unanimous. These communities are the units for creating paradigms, but paradigms are not essential for the development of an isolated community. Indeed, in this sense, the scientific community consists of a global community of scientists, which is then narrowed down into specialised scientific communities. This is brought home when Kuhn tells us that there was no physics community before the mid-19th century, when it was preceded by an intersection of philosophy and mathematics. Kuhn also notes that theories of matter were under discussion by a number of different communities. Kuhn describes the transition that occurs during a paradigm change. Revolution is a special renegotiation of relationships within a community which might consist of a small number of people. Crises can be generated by groups other than those that experience them. Kuhn suggests that his description of paradigm is vague and develops his argument with the use of a disciplinary matrix. In the disciplinary matrix there is the symbolic representation, the shared belief, and the values of the scientific community. We can ask the question, are Kuhn's assertions supported or challenged by 21st century neuroscience? In the Postscript, Kuhn discusses visual perception. Are the sensations of two viewers the same? There is a lot of processing involved in becoming aware of sensations with different pathways from stimulus to sensation. I think perhaps it is easier to talk about perception than sensation, which occurs at an earlier stage in the process. Kuhn is therefore asking us to consider whether two people or communities with their different backgrounds would experience the same perceptions of identical stimuli as though they are living in different worlds. These different groups are of course the different scientific communities with their different models of phenomenon. Kuhn's arguments aren't meant to be interpreted in a concrete way, but I thought it was a useful example of how Kuhn's material can be engaged. There was a recent study by Gallant and colleagues from 2011 which I thought was a really great study. I won't go into it in too much detail, but will summarise it by saying that the researchers were able to correlate the activity in one brain region, the visual cortex, with moving images witnessed by their subjects. They were then able to reconstruct witnessed moving images on the basis of the brain activity alone. In one of the videos, the reconstructions from 3 subjects can be seen. Above the 3 rows is the video that was shown to the 3 subjects. Then there are 3 rows, each of which corresponds to a subject. The first video in the row represents the video that was reconstructed from that subject's brain activity by the software. The remainder of the videos on the row are those witnessed by the subject, which were the nearest matches and which were averaged out to reconstruct the video. What is meant by nearest matches is that the brain activity of the subject when witnessing those videos was similar to the brain activity when they were witnessing the test video. By this means, the researchers approximated the video clip that the subject was watching, and in effect were able to reconstruct the video the subject was watching on the basis of their brain activity alone, a quite remarkable achievement. In returning to the question posed by Kuhn, it is clear that each subject's reconstructions draw parallels with different sets of images that they had been exposed to. The software algorithm selected different movie clips for each subject to approximate the pattern of brain activity that was generated when they viewed the clip of interest. Unfortunately, there is a limit to how much we can infer from these results, particularly as they result from a function of the software algorithms that were being used. However, we can also use these results to comment on Kuhn's analogies in several ways. First, we can say that Kuhn may indeed be correct in assuming that different people perceive the same stimulus on the basis of different past experiences, and this is why the three subjects in the second video appear to be drawing on different previously witnessed video clips. Remember, though, that they may be an artifact of the software. However, we may also say that regardless of the previous experiences, the subjects are operating in the real world, and this is an important constraint. Subjects can use as many prior experiences to shape their perception of the stimulus as they want, but unless they get their perceptions right in certain important ways, they'll be walking into the proverbial lamppost. Finally, we can also say that the perceptions that appear to be occurring here are doing so in real time, and in some ways are perhaps still at a fairly low level in the perceptual apparatus. The filtering is almost immediate and doesn't suggest the type of rich context and abstract reasoning qualities we might associate with some of Kuhn's concepts. The visual cortex wants to discern form, colour and motion. Kuhn's scientists want to discern the world constrained by the limits of a model built up of multiple logical inferences and empirical observations. However, the point is that Kuhn has powerfully invoked the inner experiences of the scientist, and once this is granted, the subsequent discussion must become entangled in questions about conscious experience, about the very nature of the mind. Nevertheless, the question of science is inextricably linked to questions about mind, since science is a function of the mind. Although a set of laws may quite correctly describe certain features of the universe, it is only through the mind that these laws become alive. Without the mind, they are objects, ink on paper, etchings on stone, or electrons passing through circuit boards. And to become alive in the mind, the laws, the whole corpus of science, must negotiate the mind in order to become alive and relevant in the world. Appealing to the mind is part of the package of science, whether it is recognized or not. Incommensurability, puzzles and values. If I was to read Kuhn's Postscript next week, I would probably write a very different review because of the way in which his material must be engaged. For this review, there were a few concepts that grabbed my attention. Kuhn talks about incommensurability. This is the phenomenon through which scientists from different communities have models which explain the same phenomenon, but which entail different incompatible languages. This is one phenomenon for which Kuhn appears to have been criticized vociferously. Ironically, he is clear that his concept has not been understood. Kuhn's science has been labelled as subjective, or suggesting that there is no truth in science. However, we may say that Kuhn and his critics' model of science are incompatible. Part of this incommensurability arises from science as a function of the community. Kuhn talks about puzzle solving, which was a key feature of his work. Kuhn's idea is that there is normal and revolutionary science. Once the revolution in science has occurred, the puzzle solving of normal science takes place. I like Kuhn's framing of the puzzle as a group licensed way of seeing the world. Finally, I thought Kuhn's further discussion of values was interesting. Kuhn asks us to consider what would happen if consistency was not a value in science. At such times, it is clear that science can be deconstructed in a more profound way, and that such analysis could even result in a more productive reconstruction. Kuhn's work is a magnus opus, an illustration of the rewards of the seemingly abstract discipline of historical analysis, which shows that looking closely at what has gone before can light the road ahead.